All right, good evening, class. This is the final presentation that I'm going to do for the dimensioning process. Okay, so the first presentation was an overview of the dimensioning assignments and a little bit of background of what you're going to be doing. The second presentation was the longer one, and that was the lecture of Chapter 8 in your textbook for the basic dimensioning. This is going to be kind of a continuation of the last lecture on Chapter 8, basic dimensioning. And in this one, I'm going to try to clarify and present to you a method to dimension, okay? A method that you're going to use to dimension parts in engineering drawings, okay? It's kind of a simple, I guess on the surface, it's kind of a simple method. There's basically two steps, but conceptually and practically, it takes practice, okay? It takes an understanding of what you're looking at in the part. But this is going to be the guide going forward, okay? So when you're dimensioning your drawings in AutoCAD, this may be the presentation that you want to have up next to AutoCAD so that you can kind of follow this procedure, because I think this will really help you to dimension properly and to make sense of your drawings. Okay, so let's get started. The Foolproof Guide to Dimensioning. All right, so we already talked a little bit in the first presentation about what an engineering drawing is. An engineering drawing is a means of communication. It's a technical document that is intended to communicate to various people in manufacturing and in other areas. It's intended to communicate the design of a single part. Not only the design, but the instructions for manufacturing that part. So really, an engineering drawing has a very straightforward purpose. An engineering drawing is a complete set of instructions on how to manufacture a single part. Okay? Now, in that drawing, there's different elements. All right? The first element of an engineering drawing is the shape description. All right. So in that part of the engineering drawing, we're describing what the object looks like. And the engineering drawing is standardized in such a way that we are going to describe that shape using orthographic projection, because that introduces the least amount of distortion. Actually, it introduces zero distortion, as opposed to like a three-dimensional view or anything confusing like that. So the shape description is done with the orthographic views, and that includes any auxiliary views and any section views. Okay, so the view part of the drawing describes the shape of the part that we're trying to manufacture. The second element of an engineering drawing is the size description. Okay, so if we just have some geometry on a drawing, we don't know how big it is. We don't know how big the hole is, how long the part is, how thick it is, anything like that. So in order to convey that information, in order to communicate that clearly to manufacturing, we need to use dimensions and tolerances. Okay, and so that's how we describe the size of the different features on the part and of the part. Okay. The other element that we include in an engineering drawing is notes. The notes typically are, size description kind of things, although they don't have to be. They can also describe different features and how the surface finishes or whatever. But, basically, an engineering drawing is a communication between the design group and manufacturing for how a part is going to be manufactured. All right. And that takes basically two features, shape description and size description. And right now, what we're looking at is the size description part of it, the dimensions, okay? All right, so as we discussed, engineering drawings have two objectives: describe the shape of the part, describe the size of the part, okay? The dimensioning accomplishes the size description. Here we have an example of a completely dimensioned part. All right. And here I just want to go through the different elements. Okay. So first of all, the shape description. We can see from this part that we have a circular type feature, which actually is a cylinder, right? It's not a hole. It's a cylinder. And we can see the outline of that, the thickness of that right there. All right. And the circular size of that. And then we have another cylinder positioned on top of that, a smaller cylinder right there. Okay. In the first larger cylinder, we have a square or rectangular notch cut into the left side of it. We also have 4 holes positioned around the perimeter. And then finally, we have kind of a inclined surface, what we might call a chamfer, on the smaller cylinder. So that's the shape description. The front view and the side view describe how this part looks in terms of its shape. All right. Now, the size description, because we obviously need to know the size of this, we can see that the larger diameter has a diameter, or the larger cylinder has a diameter of 75, and it has a thickness of 10 millimeters. We know this is millimeters because it says down here metric. Okay. The smaller cylinder has a diameter of, and here we have 2 dimensions stacked on top of each other. This is a tolerance, right? This just describes how accurate the manufacturing process has to be for making this. But we can see basically the diameter of the smaller cylinder is a 25.5, if we go right in the middle, 25.5 millimeters. And the thickness of it, well, it's not explicitly given, but we know that it's 20 millimeters from the bottom surface all the way to the top. Okay. So that's the 2 cylinders described. The rectangular notch cut out, again, we're dimensioning it with a tolerance. So it's 18 to 19 millimeters across here. All right. And the depth of the cut in this notch is not, again, explicitly defined in this direction. We see it from the back surface, so it's 67 millimeters from here to here. All right. Then we have the 3 holes. And again, if you remember from the first presentation, we have 3x. That means 3 holes, 3 times. A tolerance here. So 1, 2, 3. And each hole is located using these funky dimensions with the squares around them. I don't want you to get bogged down into that. This is actually what's called geometric dimensioning and tolerancing. It's a high-level tolerancing process, but we can ignore that right now. So basically, the holes are positioned relative to their centers, 23 millimeters above and below, and 22 millimeters to the left, and 31.8 millimeters to the right, again, from the center. And finally, the last feature is we have this chamfered surface or chamfered edge on the smaller cylinder. And we can see here, if you remember again from the first presentation, we have 2 by 45 degrees. So what that means is 2 millimeters. So that distance right there is 2 millimeters by 45 degrees. So that angle is 45. This is often misinterpreted as 2 times 45. It's not times, right? There's a space in that X. And it doesn't mean that there's 2 chamfers. There's one here and there's one here. No, there's only one chamfer. It goes all the way around. It just looks like 2 from this view. Okay. So, that's the drawing, the engineering drawing of this, the shape description and the size description. All right. You'll see that there's one note down here for the tolerance, all intolerance dimensions plus or minus 0.2. Okay. Again, we don't have to worry about that because we're not doing tolerances. Let's look at another drawing and kind of go through again shape description and size description. So shape description, again, we see a series of stacked cylinders. We have the circular view of the cylinders here, and then we have the rectangular view of the cylinders here. And we have a hole going through from the front end to the back end, and then the hole widens out right there. All right. And obviously this is a full section, and we see the cutting point line here denoting where the full section is. Even though, as you learned from the last module, that the cutting point line in this case is optional. All right. So then we also have 8 holes around the perimeter of this, and I can see the dimension right here, 8 times diameter 8.1. So there's 8 holes of a diameter 8.1. They're positioned around a diameter 86 bolt circle, and that's just the term used to describe the location, the center of the circles around which the smaller circles are arranged. All right. Then if we go over to the left side view here, we can see the diameter of the hole going through is diameter 20.13. Again, this is a metric drawing, so it's 20.13 millimeters. And it widens out to a diameter 44.6 hole. All right. And then we have the dimensions for the series of stacked cylinders. So the smaller cylinder on top is a 31.8 right there. All right. Then we have this kind of interesting little feature around here. Remember that this is a cylinder, so these go around the perimeter here. And we haven't really discussed this yet, but this is a symbol for a thread. So actually, this around the perimeter right here, right in this location, are threads. Okay? And the thread dimension is an M42 by 1.5-6G. What that basically means is that it's a metric thread, 42 millimeters in diameter, and it has a pitch of 1.5 millimeters. So the distance between each thread is 1.5 millimeters. And the 6G is just the tolerance on that thread. All right, that's not really important. Again, right now we'll cover threads in a couple of modules, I think. And then the other dimensions are just the positioning or location of each one of the cylinders, so that we know where they lie. Okay, so again, if we look at the drawing, if we look at the part and we break it down into its shape and size description, you can start to understand what your job is going to be. Once you get the drawing shape defined using the orthographic views and section views and auxiliary views and all that stuff, then you're going to turn your attention to the dimensioning part of it. Okay, and you're going to approach it just like you did, or just like I was talking about, with understanding what the basic parts are. And that's really where our process for dimensioning starts. Okay, so the process that I want you to follow for dimensioning, for applying dimensions to a drawing, is a very straightforward, I'm not going to say simple, but it's a very straightforward 2-step process. Okay, step number 1, I want you to dimension the sizes of the individual geometric shapes on the part. Okay. Step number 2, I want you to dimension the location of those shapes with respect to mating surfaces and functional requirements. Now, I underline that last bit because that's something that's a little bit challenging to do, because we don't often know what the mating parts are. Okay. Understand that most of the time we're drawing parts that fit into an assembly. They're part of a machine, right? And those parts are going to have other parts mating up against them, sitting up against them, resting on them, inserted in them, inserted around them, whatever. They're going to have mating parts. And so when we have those real life parts, they're going to have mating surfaces, and functional requirements just means, what is that part doing in the machine? Is that part intended to stay stationary, be supportive? Is it supposed to move? How is it supposed to move? Is it supposed to rotate? Is it supposed to slide? All that good stuff. Needless to say, we don't have a lot of that information, especially in this class. In later classes, we try to define that a little bit closer. But so suffice it to say that for step number 2, we're going to be making up some stuff in terms of the location of the shapes. All right. Or excuse me, in terms of the mating surfaces and functional requirements. Okay. But I'll help you understand what that is. Okay. So step number 1, dimension the sizes of individual geometric shapes. Step number 2, dimension the location of those shapes. All right. So let's see how this is done. So basically what you're going to do is you're going to visually, in your mind, you're going to break down each one of the parts into a series of geometric, what we call primitives. Okay. So in this example, you can see this part here, we've broken it down into a series of primitives. Those primitives are a cylinder, a hole, which is just another cylinder. We might call it a negative cylinder if this is a positive cylinder. A hole would be a negative cylinder. Then we have a prism, which is a fancy word for a rectangular solid, right? We can have cone, right? And well, on this, that's about it, right? So this part right here, when we put it all together or when we take it apart, what it's made up of is one positive cylinder, 1, 2, 3, 4, 5, 6, 7 negative cylinders, one positive prism, 2 positive prisms, and then a negative cone, right? Why is that a negative cone? Because it's a cone-shaped hole, right? So once we have that information, then that's going to help us dimension or apply dimensions according to step number 1. Dimension the sizes of the individual geometric shapes. So I just defined the shapes. Now the sizes of those. So here we have the size of the hole right there. The size of the other hole, the size of the cylinder, the size of the smaller cylinder here, the size of the prism, the large prism, we have a size here and a size here, and then we have a size here, right? So keep in mind that each one of these geometric primitives is going to have 3 dimensions, right? Why? Because they're 3-dimensional, right? So the prism has a length, a width, and a thickness. This smaller cylinder, or excuse me, this smaller prism also has a width. Now, notice how this is dimensioned. So this is basically the size of the prism is this size minus this size, right? And then the length of it is this size. So we can define the sizes of each shape, and then we can define their location. So the location of this center cylinder, it's located from the edge on the right-hand side, that dimension. And then these other holes are dimensioned, well, there's the location from here to there, that's a location dimension, and there's another location dimension. In this direction, the locations are dimensioned from the center of the object because we want the object to be symmetrical, so that implies intent on our part, design intent. So we can dimension the location from the center out here and then from the one side to the other side. And so we can go through the whole part like this. Now this example is a rather complicated part. This is taken from a textbook, so I wanted to give you another one that's a little bit more straightforward, okay? So here we have a little bit simpler part broken down into its component parts. So we have a vertical prism, a horizontal prism, 1, 2, 3 negative cylinders, 4 negative cylinders, and a positive cylinder, okay? So in our drawing, this is what it looks like, our front, top, and right side view. And then we have our size and location dimensions. So the first step is always the size dimensions. So we have, let's do the prisms first. So we have the thickness of the vertical prism, we have the width of the vertical prism, and we have the height of the vertical prism. Those are all S for size. The horizontal prism, we have the thickness of the horizontal prism. Again, this dimension does double duty because now we have the width of the horizontal prism. And the, let's see. Oh, and the length of the horizontal prism. Is that one given here? It's not. That actually, that is a mistake in this. There should be another size dimension right there. Okay, do you see that? From here to here. And that's omitted. That's an error from this textbook. And then we have the size of this cylinder and the the height of the cylinder. We have the size of these two holes, 2 times diameter size. And then that's it. Those are all the parts. Those are all the features. Now we can go on to locating them. So we locate the cylinder. Here's the location from this edge, and here's the location from the back edge. And we locate these holes. Here's the location from the bottom, and here's the location from the left edge. Now you'll notice there's a lot less location dimensions, and that's very common. All right, that's very common. So once you get the size dimensions, most of the work is already done, and that's kind of why you do step number 1 first instead of doing the location dimensions. Okay, so hopefully that's a little bit more clear. Obviously, this needs a lot of practice, and when I do the example videos in AutoCAD, we will use this process, and I'll talk you through it so that you can get some examples in front of your face, so to speak. Now, when we talk about the basic geometric shapes, I already talked about them a little bit, but here's a kind of a diagram of each one of them. Keep in mind, these are called primitives. Keep in mind that each one of these can have a positive or negative shape, right? A positive shape is a cylinder that you can touch. A negative cylinder would be a hole. In the same way that a negative rectangular prism would be a square-shaped hole. Okay? So in these examples here, in these samples, I'm also giving you how you can dimension those. So remember, each of these is a 3-dimensional primitive. So that means they have 3 dimensions. 1, 2, 3. Now, if you're wondering, well, wait a second, the cylinder only has 2 dimensions. Think of the diameter as 2 dimensions in one, right? It has this dimension and this dimension kind of built into it. And then the height. So here's a truncated prism. So this is going to have more dimensions because we actually have to define kind of 2 shapes. We have to define the pyramid, which is this height, this base, and this base width. And then we also have to define the location where the truncation occurs. Okay. So this is kind of a overly complicated example here. Here's a wedge and here's a cone. The only one missing out of this, there's actually 2 missing out of these basic primitives. So there should be 1, 2, 3, 4, 5, 6, 7 basic primitives. The 6th one is a torus or a donut shape, and the 7th one is a sphere. We don't often see tori and spheres in our drawings, so that's why it's omitted here. All right, so moving right along to some more concepts that I want you to think about while you're dimensioning. Think of functional dimensioning and mating part dimensioning. Now, here again, it's a little bit difficult for us to do because we don't have those mating parts. All right, but in a big picture, these are concepts that you want to consider. All right. So when we dimension using functional dimensions and mating part dimensions, the idea is it's going to reduce dimensioning mistakes. It's going to reduce the time we spend dimensioning. It's going to make the dimensions functional. That means they're more meaningful. Same with the tolerances, which means it's going to lead to better assembly. And better assembly means cheaper parts. Okay. So this is a win-win for manufacturing and design. All right, so now we're on to the part where we are going to talk about a number of the different rules, okay? So in the last presentation and in the textbook, there's some rules, but I've kind of narrowed it down to the essential rules here. And this is the number 1 most essential rule, and that is to follow the contour rule, okay? Contour dimensioning means that we dimension, and if you look here, we have this little part right here. We dimension this 20 in this view. Why? Because we can see the contour of that feature, right? As opposed to this view over here where we're dimensioning the 20. Yeah, that's the feature, but it's kind of difficult to see what that is because in this view, it's just a line. So contour dimensioning really tries to address what view you are dimensioning in, and that will matter, all right? You'll be marked wrong if you apply your dimensions in the wrong view. You need to consider the contour of the feature, Okay. So again, for this notch, this is a negative prism right here. We have a length, a width, and a thickness, right? So the length and the width, we dimension that where we can see this shape. Over in this bad example, the 28, we don't really know what's going on. It's just two lines in this view. Notice there's no dimensioning up here, right? So this is bad. The 28, no, it shouldn't be there. Okay. Same thing for the 10. This is dimensioning to a hidden line. We do not dimension to hidden lines. Okay. So more on the rules. Eliminate redundant dimensions. You should only dimension features once in a drawing. Not once per view, but once in a drawing. The same feature in different views is still only one feature. Also eliminate superfluous dimensions. All right. That means features must not be dimensioned in two different ways. All right. Only one dimension to one feature. This was already mentioned in the other presentation, but it bears repeating. Dimension cylinders with a diameter in their rectangular view. Dimension holes with a diameter in their circular view. Dimension curves with a radius in their circular view. Okay. Some more essential dimension rules and guidelines. Do not dimension to hidden surfaces or features. That's a big no-no. Dimension features where they are shown in true shape. This is especially important with auxiliary views. Do not cross dimension and extension lines. Understand what dimension lines and extension lines are. Crossing extension lines is unavoidable. All right. Crossing dimension lines and extension lines is avoidable and wrong. Dimensions shall not specify a manufacturing method, and we make use of symmetry if it's functional. Okay. All right. We also want a dimension outside of the view. So we don't want dimensions here. This is bad. We want dimensions here outside of the drawing view. We use standard symbols in dimensions. That includes the counterbore symbol, countersink, spot face, tapped holes, and repetitive features. Like I said, AutoCAD does these symbols for us, so we don't have to generate them ourselves, which is great because that would be really a pain. Dimension repetitive features using the multiplier, right? So when we have 4 holes, we want to say 4x space diameter 0.375. We also want to dimension holes using the correct symbols. Okay. So counterbore, countersink, spot face. Remember the new spot face symbol. This is not updated. The new spot face symbol has an SF in it. Okay. Again, AutoCAD generates all these, so we don't have to worry about making the symbol. We just have to worry about using it correctly. Blind holes get a depth, right? And the depth is measured from the bottom of the cylinder or the hole, not to the bottom of the conical tip. Slots and chamfers. All right. We talked about this in the last presentation. All right. So this is just a repeat of that. Oh, and slots. Yes, we went through all the examples for this and the importance of having the 2x space R to define this as a circular radius. All right. So now let's look at an example here. Okay. So here we have an object, and let's just break this down into its component parts. Again, we have a vertical prism and a horizontal prism. We have a very short cylinder right there. We have a hole going through the whole thing. You can see the hidden line here. Oh, and we have another hole right there. And then this has kind of a curve to it, so we got to take that into account. That's a curved top. And then we have this kind of square notch over here. All right. So let's see how we can dimension that. So the first step is to dimension the sizes of the different features. Okay. So here's the size of the prism. We have the length and the width and the thickness. And then we have the thickness of the vertical part. Okay. Now the height of the vertical part, we're not going to dimension it to the top of the curve because that's not very useful. Because it's a curve, we want to dimension it to the center of the curve. Okay. So the size of this hole, now notice this hole, diameter 13, is the same as this hole. So we can say 2 times. And then we have the cylinder here. And we have the thickness of the cylinder, 3. And we also have this square or prismatic notch, right? It's 4 thick, 38 wide. And how long is it? 89. Okay? So those are the size dimensions. We're only missing one part here, and that is the size of this curve. And that's given with the radius. So those are all the size dimensions for this part. Now we just have to locate certain features. And I can already tell you what we need to locate. We need to locate this cylinder and hole. We need to locate this hole. And that's about it. So let's see. There's the location of the cylinder and hole from the front surface. There's the location of this hole from the bottom surface. Now, if you're wondering where the location of this is from this direction, well, the center line implies symmetry. And so the location of the cylinder and hole in this direction is exactly half of 54, right? Because that line of symmetry defines that. And then we're done. Okay? So you can see by breaking it down into those that two-step process, it really simplifies things. And it also gives us a way to account for different things, almost like a checklist. So it's a super, super good, important, critically important method to understand and to utilize. Okay? So I really want you to work on that in these assignments. All right, a couple things that, frankly, this is more important if we're doing tolerances, but there is a difference in the way the dimensions appear in the decimal inch system or the metric system. In the decimal inch system, we show trailing zeros. In the metric system, we do not show trailing zeros, but we show leading zeros, okay? So it basically means that in the decimal inch system, you'll see a 0.500, not a 0.500. And we don't, and we have trailing zeros. So 10.00, that's correct, not 10. In the metric dimensioning system, we basically flip that. So leading zeros are shown, 0.5, not 0.5. And trailing zeros are not shown. So 10, not 10.0. Okay. But as I said, AutoCAD is set up to do this automatically for us. So we really don't have to worry about it until we get into tolerances. And guess what? In this class, we're not doing any tolerances. All right. So that finishes this presentation. Like I said, the main theme of this presentation, the main objective that I want you to get out is the two-step process for dimensioning. That's something that you're going to have to practice. And in the next videos that I give you where I'm going to go through the AutoCAD process of dimensioning, I will go through all that again and again and again to try to give you good examples. Okay. All right. I'll see you in the next video.